We are providing this sample design project to show you the power and flexibility of Strucalc Load Tracker. This design involves a stick frame roof with the ridge beam offset from the center of the roof. The ridge beam that supports the rafters are supported over a post that will be supported by the floor system below. To start the project, let's design the roof framing. We will first design the rafters for this, starting with RFT1. They have an interior span of 16 feet and an overhang of 2 feet. Putting this information into Strucalc, including a 5/12 pitch, and using auto size, and selecting a number 2 Doug fir rafter, we find that a 2x12 will work. We will save that analysis. Now we can design the other rafters by changing the location to RFT2. These rafters are 10 feet long and have an overhang of 2 feet. We can use smaller rafters for this span, but I will keep them at 2x12s to provide the space required for insulation. Let's continue by designing the ridge beams. We will first design RFB1. We could have designed using Strucalc roof beam module and applying tributary widths of these two rafter sections. However, in this example, we will show how Load Tracker can convert those rafter loads into uniform loads in the multi-loaded multi-span beam module. This gives a more accurate design of the actual loads on the structure and is extremely beneficial for designs that are more complicated than this one. We will put in the beam span of 18 feet. Since it may make a difference in this design, we will put in the default values for typical roof beam, which include L/240 for live load deflection and L/180 for total load deflection. And because this is a snow load region, the duration factor is 1.15. Now we can add the loads from the rafters. Click the Uniform Load hyperlink, select RFT1, pick Reaction A, and because we also want to add rafter RFT2, we will continue the loading and add that rafter, and also select Reaction A. We are done adding the rafter loads. Select No and return to the main design screen. You can see the rafters we have added show up on the Load Tracker summary screen. And these rafter loads have been converted to a uniform load on the design screen. This same kind of load transfer can be applied in the trapezoid section of this module, which we will show later in this video. Now it's easy to quickly size the beam using auto size. Try a glulam beam. Click 24FV4. It returns that a 3.5 inch by 13.5 inch glulam will work for this design. Now let's size the other ridge beam, RFB2. Because the loads from the rafters are the same, I will make a copy of ridge beam RFB1 by renaming it in the location box, RFB2. Change the span length to 16 feet. Use auto size again and find that a 3.5 inch by 12 inch beam is adequate. And I'll double click it. However, to keep the roof connection simple, I will oversize this beam slightly, back to 13.5 inches deep, so it matches ridge beam RFB1. Then I'll save the analysis. Now we will size the posts that support the two ridge beams. This post will be 15 feet long. I will open the column module. Name it COL1. Put in the 15-foot length, and we will add the column loads. Select the axial load hyperlink. Add the reaction from beam RFB1 and add the reaction from RFB2 and return to the analysis. These two ridge beam loads have combined into one load. Using auto size, assuming a number 2 Doug fir member, we find that a 6x6 post is adequate for this design. We will save that analysis. The next part of the project is to design the floor framing. This level is one support beam running north to south and the floor framing running east to west. We have a stair opening in the northwest corner of the project. First, let's size the floor joists. The main joists, JST1, run over the top of the floor beam FLB3 and bear over the walls on each end. Open the floor joist module and name it JST1. Insert the joist span of 16 feet and 14 feet. I will try one of the more commonly used joists, which are eye-level truss joists, and found that 11 7/8 inch TJI 110 spaced at 16 inches on center are adequate. We will save the analysis. Joist section JST2 also run over FLB3, but stop at a crossbeam over the stair opening. We can take the JST1 design, change the location to JST2, and modify the center span to 6 feet. Hit Calculate, and find that the same joists are adequate. We will save this analysis. Now we will size the floor beams. We will first design the crossbeam for the stair opening. It has a span of 8 feet and supports the end reaction of JST2. We will open the multi-loaded multi-span beam module and name it FLB1. We put a span of 8 feet. Open the uniform load hyperlink, select JST2, and add the reaction A. We will try 1 3/4 by 11 7/8 microlamp and find it is adequate for this design. We will save the analysis. Next we will size the beam that is along the stairway. Open a floor beam design module. Call the beam FLB2. This beam may be used in lieu of one of the joists. We will enter a tributary width of 16 inches or 1.33 feet for this beam. The beam span is 16 feet and has a cross beam 10 feet from one end. Now click the point load hyperlink, pick FLB1, select one of the reactions for this beam as they are both identical, and add that to the span at 10 feet from one end. We will try a 1 3/4 inch by 11 7/8 inch beam, and we find that it is adequate. Now we are ready to design the main floor beam. It is a continuous beam with two spans of 12 feet and 14 feet respectively. We will choose the multi-loaded multi-span beam module, call it FLB3, and enter the spans of 12 feet and 14 feet. We will first design the center span of 12 feet, which has joist JST1 going across the entire span. Click the uniform load hyperlink, select JST1, and pick reaction B, and add it to the span. As you can see, Load Tracker makes it very quick and easy to add joist loads to design a beam. An even more important and critical benefit is that you get much more accurate loads on the design members, and in particular multi-span members such as joists. Most designers will base the joist loads on this beam on half the tributary width of each of the two joist spans. If that is done, you'll get a non-conservative beam load. When you base the load on this half tributary width assumption, you get a total load of 825 pounds per linear foot based on a 15-foot tributary width times a total load of 55 pounds per square feet. Now compare this with the true load using Load Tracker. You get a total joist reaction load of 1,035 pounds per linear feet, which is 25% greater, a significant amount. Now we can design the other span of this beam. It has joist JST1 varying from 0 to 6 feet, and joist JST2 spanning from 6 feet to 14 feet. Let's use the trapezoid 1 hyperlink. Select JST1, pick the center reaction, add it to the span, and set the location from 0 to 6 feet. Now let's use the trapezoid 2 hyperlink. Select JST2, pick the center reaction, add it to the span, and set the location from 6 to 14 feet. Now we can add the 2-point loads on this span, which is column 1 at 4 feet and FLB2, which is at 8 feet. On the right span, choose the point load 1 hyperlink. Pick COL1, select reaction A, add it to the beam, set the location at 4 feet. Next, let's pick point load 2 hyperlink. Select FLB2, reaction B, and add it to the span at location of 8 feet. Now we are ready to size the beam using auto size. I will choose a 24F V4 glue lamp. Auto size, and find that a 5.5 by 15-inch beam will meet those design requirements. We can now save the analysis. The next step is to design the columns supporting these floor beams. First, we will design column 2, which is the center support post for floor beam FLB3. Select the column design module, name it COL2, set the total column length to 9 feet, then click the axial load hyperlink, and add floor beam FLB3, reaction B. Through trial and error, I have found that a 6x8 number 1 dug fir post is adequate. Set this and then save the analysis. Now we can design column 3, the right end support point, or reaction C, of the floor beam FLB3. Change the column load location to COL3 and remove the existing load trackers by selecting them in the load tracker quick view and hitting delete. Click the axial load link again and pick reaction C from floor beam FLB3. Since the column is framed in the wall, I will try 4 laminations of 2x6 and find that that is adequate for this design and then save the analysis. We can do the same thing to design column 4. We will name it COL4, delete the column load, and add the reaction A for FLB3. Because it is also a framed wall, again try 4 laminations of 2x6 and we find that these are adequate. Now I will complete this project by designing the footings. We will start by designing footing FTG1, which is the footing supporting the center column for floor beam FLB3. Open a footing module and name it FTG1. Click the live load link and all the members throughout this project will show up. Select COL2 and quickly design the footing based on the estimated footing width. Select a 5-foot square footing. Check to see if it is adequate. Save it and that footing is finished. Do the same for footing FTG3, which supports column 3. Open a footing module, call it FTG3, add the load from COL3, hit calculate to find the estimated footing size. Select a 3-foot square footing. Save it and we are done. The last footing is FTG2, which supports column 4. As you can see, you can design a project extremely fast with Load Tracker, but you will see that you will save even more time on a project if there are any changes that need to be made after you've already completed its original design. Say for example, we found out that we were supposed to design the roof of a building with 40 pounds per square feet snow load instead of the 25 pounds per square feet that we used. We can update these changes rather quickly. We will first start with the roof rafters. Let's open RFT1. Change the live load from 25 to 40. Hit calculate. We find the rafters are now inadequate. Let's try changing the spacing from 24 inches on center to 16 inches on center. Hit calculate. Now they are adequate. We will save that analysis. Now open RFT2. Change the live load to 40 PSF. Hit calculate. We find that they are still adequate. Now we will save it. Now we will check the ridge beams. We will open RFB1, hit calculate. The loads that came from the rafters have been updated and now the beam is showing to be inadequate. Hit auto size. Now we need a 5.5 by 13.5 inch glulam for this design. Now save it. Let's go to RFB2. Open it, hit calculate. We find that the original design is still adequate, but we'll deepen it to 15 inch to match the depth of RFB1. Now save it. Now we will check the ridge beam support column by opening COL1. Hit calculate, and we see that the 6x6 column is now inadequate. Let's auto size, trying a number 2 dug fir member. We find that a 6x8 or 8x8 post will work, so we choose the 6x8 and save that design. Now we can move down to the main floor framing. Looking at the plan, no changes were made to the floor joists or the beams surrounding the stairway. However, let's check for floor beam FLB3, which carries the roof support column, COL1. Hit calculate. We have found that this beam is still adequate, but not by much. As the designer, you have the option to size the beam up or leave it the same. I will use the same beam and save the analysis. Now we check the support columns. First, COL2, hit calculate. We find it is still adequate, and save. Open COL3, hit calculate, and save it. And we will do the same for column 4. We can now check the footings. Footing 1, as you can see, is still adequate, as is footing 2 and footing 3. As you can see, it only took a few minutes to recalculate this entire project. We have now completed designing all the main members for this project. You can now use Print Project to print the results of all the members designed for this project. To get a summary of all the load trackers that were used in this project, on the menu bar, click Load Tracker Summary Report. This report, which you can print out, shows all the loads you transferred using Load Tracker and includes beam loading diagrams of each of the designed beams. We are in the process of putting together an auto update feature that will cycle through and check the calculations of all the affected members in the project and let you know which members may have become inadequate due to a design change. This concludes our demonstration of the power and versatility of Load Tracker, but comes with a warning. Once you get a chance to use this feature, you will never want to manually track loads through a structure again. Our experience in using this feature is that you will be able to cut the design time in half or more on a typical project, and at the same time provide a more accurate design. We encourage you to try Load Tracker and see how it can greatly add to your design experience. We are confident that you will find that it will save a significant amount of time in your designs, but will also make the experience less tedious and much more enjoyable. As always, software design release dates are forever changing. However, barring any unforeseen design issues, our target date for the release of the beta version of Load Tracker is early November, with the full release going public in December. Thank you for watching this video, and we hope Load Tracker will be the perfect tool in helping you complete your projects quickly and easily.